I want to prove some properties of circles. Because other than triangles, circles are probably the most important figure in geometry. And in case you haven't noticed yet, almost everything we've been doing up until now has to do with triangles. Now we're going to start looking at circles. That doesn't mean we're going to be leaving triangles behind. So let's look at two important properties, and what I'm going to prove and what I'm sort of not going to prove. So the first one, and the one I'm not going to prove, is that if we draw a tangent line to a circle, and that's what we're showing right here, a tangent line to a circle. Okay, so here's our tangent. And the tangent is this line which touches the circle at one point, and that point being right here, but it only touches the circle at this one point. It doesn't enter the circle and go inside the circle. Now it turns out that if we draw a radius from the center of the circle, let's say it's here, out to the tangent, that the angle between the radius and the tangent is always 90 degrees. And as a sort of a justification on this property, rather than a proof, what I'm going to say is that, if we have a straight line and we draw the perpendicular to a straight line, so here we have a straight line, and the shortest distance between any point in space, so here's a point right here, the shortest distance between that point and the straight line is not going to be a line that meets at some obtuse angle, or acute angle for that matter. The shortest distance between this point and the line is always defined by the line which intersects the second line at 90 degrees. So this line right here, one that intersects, that goes from this point to this line and intersects this line at 90 degrees, is always the shortest distance from here to there. Now a circle, we define it being all the points that are equal to the radius r away from the center. So all these points are exactly a distance r from the center. So if we none of these points are closer or farther away than the distance r. So if we are going to draw a line from the center of the circle to this tangent, okay, then the line which is shortest is not just any line like this, but it's always the line that comes down and meets it at 90 degrees, just like that. And that line is going to be the radius to the circle, because that's how we define the distance from here to there, by the perpendicular distance. So that's not really a proof, but I'm not going to do the proof. It can be a little bit technical, and I'm not sure that it adds to our enlightenment of geometry at the high school level. Okay, but this property is something that is pretty interesting, and I am going to attempt to prove. And that is if we inscribe a triangle in a semicircle. So by semicircle, I mean that this line right along here is in fact a diameter of the circle. So if we inscribe this triangle is then inscribed in this upper semicircle of this circle. So this distance that we look at, this distance from the center to touching the circle right here, this distance is 1 radius. Okay, so this is radius r. And the distance from the center here to the edge of the circle is also 1 radius. So here I have a triangle inscribed in the semicircle. This distance is a radius, this distance is a radius, and I'm going to draw this red line from the center to this point on the circle. So this is also a radius. Now what I'm going to do is define this angle here to be A, okay, this angle here to be B, and this angle here to be C. And for lack of a better term, I'm going to call this point here right in the center of the circle D. So what do we know? We know that the interior angles of a triangle are going to be 180 degrees. So that means an angle A plus angle B, which is this angle right across here, plus angle C, which is this angle, that the sum of these three angles is 180 degrees. So let me write this down, is that A plus B plus C is 180, okay, 180 degrees. Now, because I know that the length of this line is R, this line is R, and I know that the length of this line is R, it tells me that this angle right here and this angle right here are equal. I'll call this angle B1. So this is angle B1. And this angle right here, I'll call that angle B2 inside there. So I know that A plus B1 plus this angle right in here is 180 degrees. So I have angle A plus B1 plus this angle is 180 degrees. However, I know that angle A must equal angle B1 because those are two opposite angles in an isosceles triangle. So I'm going to say that angle A equals angle B1. Now up here I have another isosceles triangle. I have this line here R and this line here R. So it tells me that this angle, well, which is B2 by the way, this angle is B2, this angle is B1. So I know that angle B2 is equal to angle C. So I have A is equal to B1 and C is equal to B2. So one isosceles triangle gives me A is equal to B1. The other isosceles triangle gives me that this angle, which I'm calling B2, is equal to angle C. So I have A plus C is equal to 180, A is equal to B1, C is equal to B2. And I also know that B1 plus B2 plus B2 is equal to B. Okay, so I have A plus B plus C is 180. So let's combine these equations together and see what we got. Okay, I have A is B1 plus B plus angle C, but C is B2, is equal to 180. Let me rearrange these so I can say that B1 plus B2 plus B is equal to 180. But B1 plus B2 is equal to B. So these two right here sum to give me B. And so I have B plus B equals 180. That's 2B equal to 180. Then it must be true that angle B is equal to 90 degrees. So we have proven that if you inscribe any triangle into a semicircle, so any triangle that is inscribed inside of a semicircle must be a right triangle where this angle right in here, B, is equal to 90 degrees. That's a really interesting property, I think. So we'll be doing more about circles as we go along.